Okay, well, we're down to our final section of course material, and it's in some sense kind of revisiting this idea that we talked about at the very end of dealing with variance and standard deviation, talking about the spread of a data set. We're going to be looking at a slightly more granular tool for looking at that kind of spread, referencing what we call a probability distribution. We're going to be interested in one in particular, but we've actually kind of already seen a kind of probability distribution. Um, in particular, a relative frequency histogram. So if you take those histograms that we did back at the beginning of the chapter and scale them so that instead of measuring total frequency, they're measuring relative frequency, that kind of gives you a way to measure exactly how spread out your data set happens to be. So for instance, I've got one here that I generated inside Microsoft Excel for the total of rolling a pair of six-sided dice. So as you can see, it measures that we've got a roughly a 1/6 probability of rolling a 7. We've got a 1 in 36 probability of getting either a 2 or a 12. So basically, the height of the rectangle is giving us the probability that we end up with a particular result. You could have done the same thing if you scaled one of our other histograms, be it the win totals, or if you set one up for the ages of the signers of the Declaration of Independence, that sort of thing. So you will probably notice from looking at the shape of this thing that it's very, very regular in structure. So we've got the 7, and then we slope down toward the smaller numbers in either direction from that peak at 7. You might have heard this shape in some sense described as kind of bell-shaped or a bell curve of some sort. This really isn't a curve, it's a histogram, but the distribution we're actually going to be interested in looking at for the remainder of the section does in fact follow that sort of bell-shaped format, as opposed to being more uniform, like if we only rolled one die and then all of the probabilities are the same, or having a probability where the peak is kind of off to the side, like right over here at 12, which doesn't make sense for our dice example, but you get the idea. So we refer to these sort of bell-shaped data sets as being what we would call normally distributed. So there's technically a whole bunch of them. So one possible example of a normal distribution that I like to reference kind of classically is IQ scores. So when the IQ scoring system was initially established, my understanding is that it was supposed to be set up as a normally distributed data set with a mean value of 100 and then a standard deviation breaking things up of 15. So in this instance, you'll notice instead of having a sort of a block bar graph histogram guy, we've got a smooth curve that I generated using an online graphing calculator. So it references a lot of the key features that you'll see out of these normally distributed data curves. So we've got this peak sitting right here at our intended mean. We got a bump right there, and then it kind of flattens out as we move out in either direction from there. So that's kind of the idea of what's going on here. And the thing that we're going to be referencing, and you'll see it in a later slide, is these curves that we use to assess these normal probability distributions are designed specifically so that if we want to know how likely it is that if we were to pluck a random person out of our data pool, so for instance, if we want to know how likely it was that somebody had an IQ score between 100 and 110 here. So if that's what we were looking for, the idea is the probability that we pick out somebody in there matches up exactly with the area of this region between those two vertical lines. So if you imagine shooting a line up from 100 along the horizontal axis, same thing right there, and measuring that area right there, that would tell you the probability that we grab somebody, at random who happens to fall into that particular range of IQ values. So on the other hand, if you were wanting to find somebody who has, say, a genius level IQ of 140 or higher, they'd be over here in this little tip between the 140 line here and that tail that's off to the far right. Obviously, it looks like a very small area that translates accordingly to a very small probability. So it turns out a lot of data sets behave following the sort of normal, bell-shaped structure. We're going to focus predominantly on looking at one in particular that you'll often hear referred to as the standard normal probability distribution. You'll notice from looking at the axis, things have adjusted a bit. So the idea here is For this standard normal, we assume we have a data set with a mean of 0. So notice the peak is sitting right there, at the along the vertical axis, and then a standard deviation of 1. So that's coming out right here. We've got a vertical line going up at 1, that sort of thing, moving on outward. You may recall from the end of what we talked about when we were discussing standard deviations that I said that for quote unquote nice data sets, we had those certain percentages of data that live within 1, 2, or 3 standard deviations of the data set's mean. Surprise, that's those are numbers that correspond to normally distributed data sets. So the idea is if you were to measure the area going from this line at -1 to this line over at a +1, that total area would measure to be 0.68. So you have 68% of your data living in that particular window. Same thing if you go out, from -2 on this side, 2 standard deviations away from 0 on one side, 2 standard deviations away on the other. You've captured 95% of the data, 95% of the area. Okay, so that's sort of the idea here, and we'll play around with this in some examples momentarily. But before we get to that, I wanted to lay out sort of some base properties that this particular graph happens to have. For the record, don't worry about how you would actually generate this graph. That's beyond the scope of Math 107. If you're interested, feel free to look around for some probability and statistics resources, but you don't need to know the formula I use to produce this thing. That's okay. So some properties that we've already mentioned. The standard normal distribution is assumed to have a mean of 0 and a standard deviation of 1. Yes, those are kind of contrived, but that's sort of built into the process, and you'll see why we would want to use such a contrived data set eventually. I promise we'll get there. So some other properties, you probably noticed the graph is symmetric in this instance. So if we go back to the picture, you can see, sort of the right-hand side is just a mirror image of what's on the left-hand side. So if I were trying to save time sketching this by hand, I could draw the right-hand side on my paper, fold it up, rub real hard, and then produce sort of a, mirror image over on the other side as far as symmetry goes. And we're going to end up using that symmetry a fair bit when you see how we actually calculate some probabilities and stuff using this standard normal distribution. The other big thing, and this is baked into the process again, since area under here is supposed to correlate directly to probability, the largest a probability can get is 1. That means the total amount of all area, if we measured everything under the graph from, in negative infinity in one direction all the way to infinity over on the far right, you should get a total area of 1. So that's baked in. Okay, so we've got our properties laid out. Like I said, if you need to take a screenshot of this or just have the slides open when you look at stuff going forward, that's fine. So I mentioned the key idea, we're going to end up measuring areas under here because we want to figure out, well, how likely it is if we pick out a particular data value that it falls into certain ranges. So probability translates directly to area in this instance. So that means we're going to be very, very focused on, for the rest of this section, on how we measure areas underneath this graph. Now, calculating the area directly is quite a challenging problem. It's the sort of thing that my calculus students, I wouldn't normally expect them to be able to do it in a Calculus 1 class. You need a fair amount of tools in the toolbox, so to speak, in order to do it. The good news is we're living after mathematicians and statisticians have been studying this thing for centuries at this point. So a lot of folks have done an awful lot of work calculating these areas using various schemes, and those areas are going to be given to you in a handout file that's listed inside Moodle. In our next video, we'll actually start using that handout to try to figure out how we can use the results in that file to calculate areas under the chart, which again translate directly to probabilities in this case. So that's it for this video. We'll shift back to the whiteboard to play around with some examples in just a second, so stay tuned.